We might hear a lot about how artificial intelligence is going to change the world, what it is, how it's terribly dangerous to all of us. But, at least in my personal experience, the developments that are being made towards strong AI today are much less talked about. So today, let's just go into that road towards AI and why it's going to be coming up very soon.
Ah.
Setting aside, just for the moment, superhuman, strong general AIs, let's consider what it takes just to get a normal human level AI, which, suffice to say, is already way, way beyond anything that we can do right now. So, if we imagine the human brain as sort of some kind of a machine which is able to take all of the data that we collect from the world, process it, sort it into categories, and then from those categories decide what to do with that data, that is a decent approximation of what we would need to do for a computer to do the same. And more or less, that is how we are using computers today in AI. But there's a large problem with that. That is, for a computer to know all of the categories and sort them, let alone what to do once we have it sorted into categories, it needs rules of categorization. And those rules need to be given line by line by line to the computer. So we could have one person write every rule of every category that is in existence. I mean, those rules exist. That's how categories are made in the first place. Or maybe we have a team of people try to each write a couple of rules on their own, and hopefully, when all of those rules are compiled together, it's going to be sufficiently comprehensive and just understandable enough to be a functional machine when it's all put together. It's, I mean, you could do it, but it's a Herculean task. So it really should come as no surprise that computer scientists figured out a shortcut. This is the basis of deep learning using so-called neural networks. Rather than trying to write all of the rules ourselves for how a computer should categorize information, we just give the computer a whole buttload of information already pre-sorted into the categories we believe they belong in. Then the computer uses programs that we've made for it to decide its own rules on how to categorize that information. So long as its rules on how to categorize things match the end results with our rules, so that when given a new piece of data, the computer puts that same piece of data into the categories that we think they belong in, it's a success. There is, of course, a huge problem with this. Computers' rules are going to be nigh incomprehensible to a human rereading the code, let alone trying to reverse engineer it. Just as an example, if you or I were told to describe what makes a butterfly, I think it's reasonable to say that we'd probably come up with more or less the same description. We would identify it in similar ways. But the computer just has that data, and it's going to identify them in completely different ways. It may say, for example, if I can see both antennae, then check the angle between them and compare that to the hue of the eyes. For all I know, this is actually a super, super good way to identify butterflies. But if you were asked me to, I couldn't say that it was or wasn't. And if it turns out that this is something which misidentifies butterflies, I wouldn't be able to tell you how, let alone correct it. And I said it in simple English that you can understand, using words like antenna, but we didn't give the computer that word. It looked at the data and it came up with some identifier for these antennae and then looks at the angles between them. And that identifier isn't going to be the word antenna, it's just going to be another jumble of code which makes sense to the computer, but to some programmer trying to do a bug fix and figure out why the computer keeps thinking that bees are butterflies, you can't do it. It's not possible. But if our eventual goal is making a computer which is smarter than ourselves, the computer code eventually is all going to be incomprehensible gibberish anyway, at least to us. No matter how carefully you try to explain it, advanced calculus is always going to be beyond the capabilities of simple chimpanzees. For reference, we're the chimpanzees in that scenario. So we let that slide. But there's a bigger issue if our goal is smarter computers. And that's that answer bank that I mentioned. See, when I give that computer the answer bank, it's programmed to believe that the answer bank is sorted correctly. So it's never going to be able to tell us that we made a mistake in its initial parameters. And beyond that, anything that we misidentify is going to be wrong. It's never going to be able to make a new category. At best, maybe it can say that this item doesn't seem to fit into any of the categories we've given it so far, but it's not going to make its own category or certainly never ask a new question. If we're smart, we can have it solve old problems in new ways, and we might be able to even have it solve a new problem so long as that problem is sufficiently similar to an old one that we feel comfortable having it solve this new problem in the old ways. But a real breakthrough is impossible for the computer. And if we tell it that this new piece of information, which doesn't really seem to fit into the boxes that we've given it so far, should fit, and put the platypus into the mammal category, it's just going to make new rules to fit that information that we just told it, even if its initial response that we probably should have done a new category is more logical, or if not more logical, just more correct. The fact is that human information as we know it is far from complete and far from 100% accurate. We have it as good as we can right now, but if we are using only old information to try to make new information, it's never going to work out for us. At least, not this way. So, in order to achieve real artificial cognition, we're going to have to do one step better than just having the computer take information given to it and process it in a known way. We're going to have to teach the computer how to think for itself. And if that doesn't sound hard enough, just conceptually, think about how hard it is to just get people to really think for themselves. And we more or less know how people think. I mean, not at some fancy fundamental neuroscience level, but if I'm presented with a problem, I can more or less assume that you and I are going to approach the problem in similar ways, or at least in one of a handful of different ways. Computers think completely differently. But maybe that's where the logic should be lying. That rather than trying to focus so much on the intelligence of the computer, instead focusing on how humans think and trying to emulate that. At this point, I've found two major projects working on this sort of simulating human cognition. The first is really a sort of empathic artificial intelligence system. Using whatever programs that we've given it, probably something with deep learning and neural networks, it takes the information that we give it And then, rather than just process that information on its own, it predicts how it thinks another mind would process that information, takes the results from that, and then feeds results to us based on that. Now, you'll note that I said mind, not specifically human or computer, because a fully functional empathic system like this would be equally capable of synergizing with either humans or other computer programs, whether or not they're running the same code, so long as it can accurately predict how they're going to work with that information. As with many forays into developing an artificial intelligence system, one of our best tools in both making the program and testing it is for us to try to teach the artificial intelligence how to play a simple humans game. In this case, the game Hanabi. For those of you who aren't aware, Hanabi is sort of a collaborative card game where rather than trying to play against the other players, instead you work together to try to get a high score. Unlike regular card games, you don't see the contents of your own hand. Rather, everybody is dealt out a hand of cards, but you see everybody else's cards instead of your own, and you try to use hints given by other players to figure out what's in your hand, so you know which cards to play, discard, and then the game constantly changes as you draw new cards and so on. This is a real challenge for a computer to try to deal with, because when the computer makes a move, there's not just a single correct move from the get-go, and it's not enough to say that this card is the correct one or this is the single correct hint. It has to be able to figure out, based on this incomplete information of what it knows and what other people know, to try to think why given hints were given at any particular time. If I tell you that you have this hand of cards here, and this card and this card are blue, it doesn't give you any terribly useful information on its own. But if another card, which was made blue cards playable just a second ago, was put down, maybe that gives you more information. For you to be able to figure out what I'm trying to tell you by saying my hint, you need to be able to think of what I think you'll think I think you'll think you have when I tell you that hint. And then, thinking on that, looking at my cards and our shared pool of cards that other people have, you can reasonably make a guess of what the correct move is to do next. Maybe. But that kind of recursive thinking model is extremely difficult for computers, at least today. And yeah, being able to accurately empathize with humans, at least with that basic human logic, to be able to play Hanabi well, would be a huge step towards advancing artificial intelligence. But I said that I'd found two major projects towards simulating human intelligence in computers. The second is both more simple and then way more complicated to implement. This second method of human-like artificial intelligence is called whole brain emulation. And just like the package says, it is literally just taking the entirety of a brain and emulating it through a computer program. It's literally analogous to running Windows on a Mac, or rather, I should say, a Windows emulator through your Macintosh program. The computer takes the data given to it, runs human.os, puts the data through human.os, human.os compiles the data, figures out some stuff, gives that data back to the computer, and the computer gives it back to us. Okay, so in that way, it's simple. It's just taking a human brain and putting it into a computer. Which, I just said that line out loud for the first time, actually, and it's some crazy sci-fi stuff. You're putting a human brain into a computer. Okay. So obviously this is complicated, and not least of all because of the huge processing power required to do this. For every neuron that we want to simulate in the computer environment, we need to be putting a whole bunch of processing just into holding that neuron in place. And then we're going to network that with a bunch of other neurons and run synapses through this in order to figure out how problems work. The amazing thing is that we can do this. I'm not saying we theoretically believe we can do this. We know we can do this. We've done it with flatworms. Flatworms, for reference, have an amazing 304 neurons in their brains. That's a little bit less than humans, but even so, we've been able to simulate neurons on a computer and put together this simple brain, put it into a robot, and without giving it any extra commands, the robot behaves like a flatworm. If you didn't know that it had happened, if I hadn't heard about this myself, I wouldn't believe that's possible. But we have done this. The issue is that with each additional neuron that we add on, the processing requirements increase exponentially. And flatworms have 304 neurons. But as I said, humans have a little bit more. Humans don't have 304 neurons. Humans don't have 304,000 neurons. No, a human brain has something on the order of 86 billion neurons that we would have to simulate in order to have a human brain, whole brain emulation work correctly. And that's a lot. The amount of processing power for that is worlds beyond anything that we have currently. And we can't just pick out the logic centers of the brain. We don't understand human brain neuroscience nearly well enough to know what parts of the brain are critical in order for logic to work. And then, once we've been able to perfectly scan a brain down to the cellular level, get those neurons, get a computer that has all of them processing, working all together, we get into other issues. We've just put a human brain into the computer. As said, it's not a part of a human brain. It's a human brain. And that human brain is, right now, a blank slate. It doesn't have any memories or knowledge. It's not going to be able to do calculus, even though human brains are able to do calculus, because it's not programmed to. Well, no more so than any other human brain. Actually, that might not be true. Maybe it can do calculus because we need a starting model. We need an actual human brain, not some blank slate generic brain to do the scans of. We might be putting Albert Einstein into a computer. But again, it's not just a computer knowledge equivalent of Albert Einstein. As far as that computer is going to be concerned, it is Albert Einstein. How do we deal with things like the computer's drive to eat, to drink water, sleep, to make friends, to stimulate itself? How do we do this? I just don't even have the words to describe the kind of problems that this deals with, just on a technological side, let alone morally. And even if we're able to somehow get rid of inconvenient things like personality and personal memories, and we're able to program in language and the ability to do math or science, even then, we only end up with a human level intelligence. Nothing crazy fancy. So, what do we do with that? Why not just use our own human intelligences at that point? Now, to be fair to whole brain emulation, the difference between 304 neurons that we've done so far and 86 billion is a lot. In the process of upscaling towards 86 billion neurons, I'm willing to accept that there's some possibility that we figure out these problems. Maybe we are able to make an actual blank slate human computer. Or maybe we're able to do better, just get the logic centers. And maybe we're even able to make a smarter human brain simulated through the computer, whether by carefully adding neurons in carefully chosen places, or maybe we do something fancier and just make the neurons better. Which all leads us, actually, to the last way that I'm going to discuss, at least for today, how we achieve artificial intelligence. And that is, if we're going to augment the brain already in the computer, why not just augment our own brains? Don't click away. Hear me out. I know it sounds crazy, but we're already well on the way towards doing this. I already have a computer which I carry around with me every day, through pretty much all of the day actually, constantly using to talk to people, do information gathering, calculations, remembering things. Of course I'm talking about this little guy. Cell phone. I think you probably have one too. It's really handy. I can have it save dates for me, pictures, video. It will do anything for me that I need it to, including talking to people, calling, texting, sharing information, calculations. All it would take is for somebody somewhere to find an interface between computer and brain, and suddenly that personal computer that I take with me everywhere isn't just something that I carry with me and use. I might be able to interact with it at the level of thought. I think, what's 2 times 8? And rather than pulling up a computer software, it just has a built-in function, much like if I say, hey Siri, what's 2 times 8? It supplies 16, except since it's connected directly to my thoughts, it provides it as though it were a natural thought. I just know it's 16. Or maybe I know 5,738 times 6 is, I actually didn't do that beforehand, I don't know. But this computer augmented person could. And that's the point. They'd be able to do things that to us seem crazy, but aren't actually beyond human level, or at least not beyond human level with a little bit of aid. What's going to make this the potential to go beyond, to reach strong AI levels, is that sooner or later, if I'm hooked up to my computer, I really believe someone's going to make the program that sooner or later says, hey, if I put in this string of code, it's just going to naturally augment my ability to think by, call it 3%. Not a lot, but I'm smarter than I was before implementing that code. And using my new intelligence, maybe I'm able to make another little augmentation and make myself 3% smarter than that. And that. And again and again. And before very long at all, we have people augmented with technology who are miles beyond any level of cognitive ability that prior humans had been able to reach. I'd actually really love to go into this more right now, but already this video is so much, very much longer than anything I've put out so far. So I'm going to leave you with that to think on. And if you're interested in any of the stuff that I've spoken about so far, I'll leave links down below to the open project for AI Hanabi, towards Flatworm robots, and also if you're interested in looking into human augmentation, there's various great works of speculative fiction on the subject. And my list by no means is comprehensive. If you know any other great works that you'd recommend on the topic, I'd love to hear about it down in the comments. And if you enjoyed the video, as always, give it a little love. Thumbs up, like, subscribe, comment. You know the drill. And until next time, see ya.